All right. Well, hi. Welcome back to the new reality, which is hopefully only temporary. Maybe we'll get some, I don't know, tests, data on who's sick and who's not, and then we can go back to repairing the economy and hanging out together and spreading germs without fear of getting sick, which I guess we've always done. Uh, you've heard it 1,000 times, but please take it to heart. If you are young and blessed with a good immune system, please be conscious of those who aren't. People with compromised immune systems, including elderly people, don't sweat on your grandma, but also strangers. Like you don't know what's going on inside people's bodies, so give folks the respect of a little bit of space. But and importantly, please don't get information from me. Don't get information from a teacher or a family member who speaks with authority and claims to know things. I'm an astronomer. I don't know anything about viruses. Go to the experts, the Centers for Disease Control and Prevention. Here's a link right here, which you will not be able to click on because I don't know how to do YouTube that well yet. But the link will be in the description, so there we go. I know how to do that. I can put a link in a description on YouTube. I'm a Gen Xer. All right. Well, we are having class. It will proceed. Oh, here we go. Okay, is that good? Come on, get off. Oh, whatever. I'll move this over here. All right, fine. Hi. There we go. All right, first off, everything here is subject to revision. Just still figuring out what we're doing. So first off, classes will be recorded, not live. And the videos of the class will be uploaded to YouTube. And so please, right now, go to my YouTube channel and subscribe. You can find it by, I put here Googling, don't use Google, use the YouTube search engine, Physics and Astronomy with Dr. Doug Shields. In fact, let's do that right now. We're going to go to YouTube, go to the YouTube, as Bernie Sanders calls it. T.O. Bernie. And we will type in physics and astronomy, eventually, okay, not zone, with clearly not enough people have looked for my page yet. Dr. Douglas, Shields, and it should be, there we go, right there, there it is. Okay, first thing you'll notice, go to playlists. There are 3 different playlists because I teach 3 different classes. So you're going to find NWACC Survey of the Universe. And right now, there's only one video on there, which is the video of me learning to record. But now, by the time this video posts, by the time you watch it, there'll be 2 because this video will be on there, which is meta. All right, enough about that. Doop-de-doo. I'm doing it on YouTube instead of on Canvas because although Canvas is good, Canvas has been really... Canvas has been reliable ever since I've started using it. However, nowadays, when all the teachers in the known universe, more or less, are going online, it might be that Canvas's servers aren't prepared for that. Maybe they are. Maybe they're awesome. I don't know. But I'm pretty sure YouTube can handle it. YouTube understands volume. So I'm going to post videos to YouTube. And then I'm also going to post a link to the files section on Canvas. So yeah, we're still going to interface with Canvas. But if Canvas crashes, we're still having class, go to YouTube. Consider YouTube a backup for Canvas. Also, YouTube is a good place to ask questions. You can ask questions in the comments and I'll answer them. So there aren't going to be any more vocab quizzes and we're not going to do a project. I'm just that one's fallen through the cracks. We still will do classwork. You will upload that to Canvas, just like homework. If it's text, please type it. If it's something with math, then please use a high-quality scanner. If necessary, use your phone, but please, use a cell phone with a good camera, and make sure you have good lighting. The most important thing here, if I can't read your work, I can't give you credit. So when you snap a picture, don't just snap a picture and upload it. Look at the picture. Ask yourself, if you had not written that, would you be able to read it? Would you know clearly and unambiguously what was written there, and so that you can get credit? Whenever students snap pictures of things and then send them to me digitally, about 1 in 10 fail, not because they did bad work, but because I can't read what they wrote. I must be able to read your work or I can't give you credit. The lecture schedule has been updated because we didn't do anything on Monday. We'll cover that in the next slide partially. But for the full lecture schedule, please go to the not the files section, the syllabus section on Canvas. Don't go to files, it's not in files, it's in syllabus. Canvas has a dedicated link to syllabus. Clearly you can see that, but if you're like me, you can look right at it and miss it. I do that all the time. I still stub my toe on my own couch. I know it's there. So in the next slide, we'll talk about the new lecture schedule. Exams 3 and 4 have been changed. Also, the semester grading scheme has been changed in order to exclude projects, because there's no project. So again, download the new syllabus for the new grading scheme. And we are going to do labs, but I'm going to coordinate with the other faculty for what we're going to do. In general, we're not going to do the NAAP labs, what we normally do, because those require Java applets, and those are tricky to get to work. I can usually get them to work in our classroom, but I can't guarantee that a Java applet is going to work on whatever random computer you might be using. So we'll figure something out. I'll figure something out with labs. I'm coordinating with the faculty to figure that out. So for the complete schedule, please download the updated syllabus from the syllabus link on Canvas. The most important changes are Exam 3 and Exam 4 have changed. Exam 3 will be on April 6th. Exam 4 will be on April 29th. And I'm pretty sure NWACC will still be online on April 6th, and it's not clear whether it will be on April 29th or not. And as those dates approach, I'll give you clues on, I'll give you instructions on how to take those exams. Final exam has not changed. It's still on May 4th. All right, well, we can't do call and response. So at least, hey, say it with me and do it out loud. Make your family nervous. Make them, whoever you're hanging out with, make them wonder what in the world you're doing. Say it with me. 1, 2, 3, parallax. Tells you how far it is to a star. Apparent magnitude is how bright the star appears from afar. Absolute magnitude is the total light the star exudes. Astronomy rocks! All right, well, let's talk about the second half of properties of stars. And to recap, how do we know these things? Well, distances to stars is pretty straightforward for the nearby stars. We know the distances to nearby stars by stellar parallax. If you move your head back and forth while you're looking at your screen, and please do that, again, the whole goal is to make your family wonder what in the world you're doing. It looks to you like the screen is moving back and forth. It's not, your head is. Likewise, as the Earth goes around the sun, it looks to us like the nearby stars are moving back and forth. They're not, Earth is. There's a small effect because the stars are really far away. It's too small to be seen with the naked eye, but with a good telescope you can measure it. This is called stellar parallax, the apparent shift in a star's position owing to Earth's motion around the sun. And if you can measure the parallax, that is, if you can measure the angle on the celestial sphere, which the star shifts due to Earth's motion around the sun, the parallax angle, then the distance to Earth is super easy. It's just the reciprocal. Distance equals the reciprocal of parallax, 1 divided by parallax. So d equals 1 over p. P is the parallax angle in arc seconds. And d is the distance in parsecs. And a parsec is about 3.26 light years. Okay, I'm trying to, what's going on here? Oh, there we go. Ha! Computer work! Yeah! Look at Gen Xers trying to use technology. Oh. All right, flux. Flux is another word for apparent brightness. They're the same concept used in different contexts, right? We say apparent brightness when we're looking at it with our eyes. We say flux when we're taking a measurement with a telescope. Same idea. Flux, or apparent brightness, of a star depends on its luminosity, which is how bright the star actually is, and the star's distance, right? So two stars that have the same luminosity, the more distant one is going to appear dimmer, and the closer one is going to appear brighter. So two stars may have the same luminosity, but different apparent brightnesses. Flux decreases with distance squared. Square the distance, square the distance, square the distance. I want this to be an earworm that annoys you anytime you take an exam. Square the distance, square the distance, square the distance. So if you were suddenly to jump on a ship and move 5 times as far away from the sun as you are now, the sun would appear dimmer, right? Because you're farther away. But if you are 5 times as far from the sun, it's not going to be 1/5 as bright. It's going to be 1/25 as bright. You've got to square that distance. If we use metric units for fluxes and luminosities, then we have to use scientific notation. They tend to be really, really, really large numbers for luminosities and really, really, really small numbers for fluxes. Astronomers do that sometimes, but more often, especially if they're just talking about stars casually, they will use magnitudes. Magnitudes are just another way of expressing both flux and luminosity. We say apparent magnitude if we're talking about apparent brightness or flux. We say absolute magnitude if we're talking about luminosity. And why the Greeks did this, I will never know, but brighter stars have lower magnitudes. So negative magnitudes are the brightest stars of all. And here's some example. One of the great advantages of the magnitude system is that it uses small numbers, positive and negative, but still pretty close, pretty small, everyday numbers, not scientific notation numbers. So the brightest star, the brightest object in our sky, of course, is the sun. Its magnitude, apparent magnitude, is negative 26.7. So there's no practical reason in astronomy that you're going to have magnitudes any lower than negative 26.7. I mean, maybe conceptually you could, but you would be talking about an object that's brighter than the sun. On the other hand, the dimmest magnitude that we're going to see, the dimmest galaxies visible to Hubble Space Telescopes, are in the plus 20s. I said 23, I think it goes a little beyond that, but the plus 20s. So basically everything in our sky that we look at with telescopes has magnitudes ranging from negative 27 to plus 20 something. Small numbers. The full moon has a magnitude of about negative 13. The brightest planet is Venus, of course. Its magnitude is usually about 4.4. All the planets vary in their magnitudes. Sirius is the brightest star in the nighttime sky. It has a magnitude of negative 1.5. Most of the bright stars will have magnitudes around 0 or plus 1. The dimmest stars you're going to see in Bentonville are plus 3 or plus 4. And the dimmest stars, if you go way off in the desert where there's very little water vapor to cloud your view and very little light pollution to glare it out, you'll see just a sky filled with stars. And the dimmest stars you will see have magnitude plus 6. If you just want to compare two magnitudes, That's pretty simple. You just subtract them. It's another great advantage of magnitudes. If you want to compare fluxes, you've got to divide. We take ratios of fluxes or ratios of luminosities, but if you want to compare magnitudes, you just subtract. However, if you want to compare fluxes using magnitudes, well, you got to do some math. And the math that we learned last time is that the ratio of the two fluxes, flux from star 1 divided by flux from star 2, in other words, if you want to know how many times as bright star 1 is than star 2, remember this fraction means than. How much brighter is star 1 than star 2? You take this base right here, 2.512, good old fifth root of 100, and raise it to the power of the difference of the two magnitudes. And remember, the magnitude on bottom comes first. That's the biggest mistake students make. They'll swap these two magnitudes out. Which magnitude comes first? It's the one on bottom. Hey, come back here. Hey, come on, technology. Do your... Thank you. Same formula applies for luminosity. You compare two luminosities by taking the fifth root of 100, 2.512, raise it to the power of the two absolute magnitudes. So where fluxes use apparent magnitudes, luminosities use absolute. Now let's talk about the temperatures of stars. Move this around. Doop-to-do. You don't want to see me that well, do you? There we go. My face is not that important here. Can we get, okay, very good. All right. There are several ways to measure a star's temperature. And in science, that's good because when you're asking yourself a question like what's the temperature of a star, where you can't go up and directly measure it, you can't stick a thermometer in a star, we can't even get to another star. So if you want to determine a quantity that's hard to measure, you want more than one way to do it, more than one independent method of answering the question. And then if those two independent methods agree, then you have confidence that you really know what you're talking about. If not, then one of the methods is wrong. You got to go back and scratch your head. And this chart right here, this figure, shows both ways that we use. One is by color. Remember, brighter stars glow bluer. Dimmer stars glow redder. So just by the color, or by the brightest color of the star, the brightest wavelength of the star, you can determine its temperature, roundabout. And the brightest color doesn't have to be on the visible rainbow. The hottest stars glow most brightly in the ultraviolet. The dimmest star, the coolest stars glow most brightly in the infrared. Our sun glows in the yellow-green. That's one way of doing it. That's a very good way to do it. But there's another way, and that's good. We need a check because you never know. You might think you have a great way of understanding something, but your theory is completely wrong. So you want an independent method to verify that. And there is a method, and that is by looking at the spectral lines. Different substances are stable at different temperatures. So by looking at what substances are in the photosphere, as measured by the spectral lines, you can estimate the temperature of the star. Yeah. So first let's look at the thermal properties. Stars glow according to two laws. One is the Stefan-Boltzmann law, which says that hotter stars are brighter. Or at least hotter stars are brighter from every square inch of their surface. So what that really means is there's two ways to have a bright star. You can have a hot star, which glows brightly from every square inch of its surface, or you can have a big star that has a lot of square inches through which to glow. The second law is called Wien's law, which says that hotter objects essentially glow bluer. Hotter objects emit photons with a higher average energy. A hotter star's brightest color will have a shorter wavelength. So let's look at this graph right here. This figure that we see is a spectrum. The x-axis is wavelength, or equivalently color. You could also equivalently say frequency. So the low wavelength end is the, the high wavelength end is the low frequency end. And then the y-axis is brightness at each color, relative intensity of each wavelength. You see the visible rainbow right there in the middle? That's exactly what it looks like. It's the rainbow, the colors you can see with your eyes, with violet on the left and red on the right. To the left over here are wavelengths shorter than violet. We call that ultraviolet. And on the right over here are wavelengths that are longer than red. We call those infrared. And we have 4 different curves here. Let's start with you, human, your 310 Kelvin body. All right, well, that's not very hot compared to a star. So you, according to Stefan Boltzmann law, are very dim. You don't glow much at all from the square inches on your body. And according to Wien's law, you don't glow very energetically either. In other words, you glow with long wavelength, low frequency. You only glow in the infrared. That's why if we go in a dark cave together, I can't see you with my eyes. But I can see you if I have night vision goggles, because night vision goggles are nothing but infrared detectors. They detect that very frequency that you radiate because of your temperature. Well, let's turn up the thermostat here, huh? Instead of a 310 Kelvin human, let's go to the dimmest star. A dimmest star is a little less than 10 times as hot as you are, 3,000 Kelvin. Well, a 3,000 Kelvin star still peaks in the infrared. Its brightest color is still infrared. But your eyes don't see infrared, so you're not going to see this star as infrared. You can't do that. What you see with your eyes is how this curve cuts across the rainbow. So this 3,000 Kelvin star throws us a lot more red light than blue light. So we will see this star with our eyes as a reddish star. Go out at night, see a reddish star, like Betelgeuse, the left shoulder of the constellation Orion, a red supergiant star. It's not a very hot star. It's only 3,000 Kelvin plus or minus, a little more than that. Well, let's crank up the temperature. Instead of a 3,000 Kelvin star, let's look at our sun, which is about 5,800 Kelvin. We're doubling the temperature now, almost. Well, the sun is brighter than the red star at every wavelength. That's the Stefan Boltzmann law. In other words, this yellow curve right here is completely above the red curve at all wavelengths, at all frequencies, at all energies. The sun, at least from every square inch of its body, from its surface, from every square inch of its photosphere, the sun is brighter. But notice that the brightest color is to the left of what it was with the red star. The brightest color of our sun is right there in the middle, yellow-green. The sun is a yellow-green star. And yet, we don't see it as yellow-green. Why is that? Well, remember, our eyes don't see the brightest color. Our eyes see how this spectrum cuts across the visible rainbow. And the sun's spectrum cuts almost flatly across the visible spectrum. So sunlight, as it reaches Earth, is almost white. Remember, white light is all colors equal. Now, here on Earth, the sun looks yellow or orange if it's low to the ground because of atmospheric effects. But when astronomers go into space, they report that the sun looks strikingly white. Well, let's crank up the temperature even more. So instead of a 5,800 Kelvin star like our sun, let's look at a 15,000 Kelvin star, 2.5 times as hot as our sun. That is an ultraviolet star. First, Stefan Boltzmann law says this star glows more brightly at all frequencies than our sun does. In other words, this blue curve is completely above the yellow curve at all frequencies, at all wavelengths, at all energies. At least it glows more brightly from each square inch of its body. Remember, a cooler star can still be a brighter star if it's bigger, if it has more square inches from which to glow. But this 15,000 Kelvin star's brightest color is not on the visible rainbow. Its brightest color is ultraviolet. It is an ultraviolet star. But your eyes don't see it as ultraviolet because you can't see ultraviolet. Your eyes see this star as blue-ish, maybe bluish-white. Why is that? Because your eyes only see how this spectrum cuts across the visible rainbow. It throws more blue light at us than red, so it's going to appear bluish. Now, this curve is not nearly as steep as, say, the red curve down here. So while the red curve is going to look straight up red or orange, the blue curve here is going to look bluish white because it's a little bit flatter than the red curve. All right, so that's a quick and dirty way to measure a star's temperature. All you need to do is look at its brightest color. And what's the results? Well, stars range in temperature from about 3,000 Kelvin up to 50,000 Kelvin, with our sun being a little less than 6,000 Kelvin. All right, that's cool. We have a lot of confidence that we understand thermal radiation because we can do it in laboratory here on Earth. We can heat gas up to hot, thousands of degrees, no problem, and watch how it glows. Yeah, no problem. We can heat things up, watch them glow. So we can do that in a laboratory, and we have high confidence. But in science, if you're going to have maximum confidence that you know what's going on, you really want at least two independent methods of measuring the same quantity. And if those two methods agree, then hey, you have increased confidence that you know what's going on. And there's another way, ionization. Different substances are stable at different temperatures. So the coolest stars are 3,000 Kelvin. And at 3,000 Kelvin, there are some molecules that are stable. Molecules, two or more atoms bound together electrically. Those are stable. Some molecules are stable at 3,000 Kelvin, and we can do that in a laboratory. We can heat molecules up and see when it gets too hot for them, when they break apart. So indeed, when we look at 3,000 Kelvin stars, we see in their spectrum spectral lines that indicate the presence of molecules. Now our sun, 5,800 Kelvin, no molecules. No, too hot for molecules. So when we look at the sun spectrum, we do not see the spectral lines that indicate molecules. What we do see are spectral lines that indicate some ions. Ions are when an atom has either too many electrons or too few. And in the case of stars, it's almost always too few. So say you have helium. Let's go to the board. I don't know if you can still hear me, so I'm going to shout at you. Neutral helium has 2 protons, usually 2 neutrons, and surrounded by 2 electrons. All right, cool. And neutral helium has a specific set of spectral lines. We can detect that in a star. But supposing this helium atom gets really hot. Well, if it does, one of these electrons will be knocked off. So then you will have ionized helium. Singly ionized helium. That means one electron has been ripped off. All right, well, singly ionized helium has its own spectrum. So we can tell, we can look at a star and say, aha, I'm seeing such and such amount of neutral helium and such amount of singly ionized helium. Now, let's heat this thing up even more, such that the second electron gets ripped off. That happens too. If this thing gets hot enough, there'll be no electrons left at all. Then you have what we call doubly ionized helium. And that's real hard to detect. So by comparing the amount of neutral helium to the amount of singly ionized helium, we can determine a temperature. Oh, what am I doing? Sure. So here is the sun spectrum. Each of those dark spots that you see is a spectral line. It is a color that has been absorbed by some atom in the sun's atmosphere. So the spectral types that we see here represent different temperatures. The ones at the top are the hottest, and notice there are very few spectral lines at all in the hot ones because they're all ionized to the point that there are practically no electrons left. And in order to show spectral lines, you have to have at least one electron. So that's why neutral helium, easy to detect. Singly ionized helium, easy to detect. Doubly ionized helium, when there's no electrons left, hard to detect because it doesn't have spectral lines. Or it doesn't have dark spectral lines. The nucleus itself can produce some spectral activity, but it's really hard to detect, and it's not on the visible rainbow. All right, so here are the spectral types, and they represent temperature. O-type stars are the hottest. B, A, F, G, K, M, M-type stars are the coolest. And on the O-type stars, there aren't very many spectral lines because the electrons have pretty much all been ripped off. They're so hot. Our sun is a G-type star. It has a lot of spectral lines, but it doesn't have molecule lines. It's got a lot of atom lines and some ionized lines as well. Ionized ions do have spectral lines as long as there is at least one electron left. But now we go down here to M. Look at all those spectral lines, because not only do you have atoms, you've got molecules hanging out inside an M-type star. Well, there's a little saying that astronomers like to say in order to remember the spectral types. Oh, be a fine girl or guy, whatever you're into, kiss me. O, B, A, F, G, K, M. O is the hottest. M is the coolest. So the folks who developed these stellar classification, they're called spectral types because they were originally discovered by their spectral lines and then later arranged by temperature. They were discovered by a woman named Annie Jump Cannon and Harvard calculators. At this time, calculators were humans, often women, who did the work, and then, the fat guy in the middle took the credit. But fortunately, history preserved the records so that we can now give these women the credit that they did not receive in their lifetime. So that's how we know a star's temperature. What about mass? How do you know how massive a star is? And before we get into the details, let's look at the simple concept behind it. You measure an object's mass by watching its gravitational influence on other objects. You measure the sun's mass by watching the planets go around the sun. You measure Earth's mass by watching the moon go around the Earth. So remember, the gravitational force depends on mass. And so you can tell the mass of something by watching its gravitational effect on something else. In the old days, this was usually stars in binary orbits. That still works, but today, in the past 20 years, we now, in addition to that, have stars with planetary systems. So if you can detect a planet around the star, sometimes you can get a good estimate of the star's mass as well. Sometimes the planet's mass, but not always. So gravity is our scale. It's our measuring device. It's our weigh scale. And that we have Isaac Newton to thank for that. What you need to compute the mass of the star is any two of the three. Orbital period, orbital radius or semi-major axis, more precisely, and the I'm sorry, my brain just farted. Boy, the orbital speed, because if you have orbital speed, you can determine the other two. So if you have a circular orbit, then you can determine orbital speed from the orbital radius and the period. And even if it's not a circular orbit, you can still compute it. Likewise, if you know the orbital velocity and the radius, then you can compute the period. If you know the orbital velocity and the period, you can compute the orbital radius, or the semi-major axis more generally. So we need two out of these three: orbital period, orbital separation, orbital velocity. So we know most of what we know about star masses from studying binary star systems. These are two stars co-orbiting their common center of mass. Because binary systems were known long before we were able to study planetary systems. Planetary systems are a new, not a new concept, but it's new that we've known that planets orbit other stars and have been able to take measurements on them. We classify binary systems not by their physical properties, but by how we are able to detect them. Visual binary, eclipsing binary, spectroscopic binary. And we'll talk about each of these specifically in the upcoming slides, but it's worth noting that binary star systems are not unusual. In fact, they are the norm. More than half of all stars are in binary systems. So our sun being the only star in our solar system isn't unusual, but it is in the minority. All right, a visual binary is kind of what it sounds like, right? It is a binary star system where you can, with your telescope, see both stars. You can image both stars and you can watch them go around each other. An eclipsing binary is one where you may not be able to see both stars individually in your telescope, but you can, it happens to be that the orbital plane of the star is in your line of sight, just like the transit method of planetary detection, exoplanet detection. The transit method of exoplanet detection and eclipsing binary detection are the same thing. The only difference is, with the transit method, you have a planet orbiting a star. With eclipsing binaries, you have two stars co-orbiting their common center of mass. But in both cases, you have one object passing directly in front of the other so that it blocks out the light. And then the observed starlight dims. With an exoplanet, usually it only dims once. But with a star, it'll dim twice. Once when a star moves in front of the other star, and again when the second star moves behind. Like transiting exoplanets, eclipsing binaries have a problem, which is that in order to detect eclipsing binaries, Earth has to randomly be in the orbital plane, right? The star has to pass directly in front of the other star. eclipsing binaries are not if a star goes like this, if a star system is orbiting this way, or diagonally. That doesn't work, right? They have to orbit such that they are directly in your line of sight. One star has to come directly in front of the other and block it out. So most binary systems don't do that. However, if it's even close to the line of sight, then you can detect it using spectroscopy, a spectroscopic binary. So you have a primary star and a secondary star. Each star has its own set of spectral lines. And as the two stars dance, as they co-orbit their common center of mass, why, they take turns. One star will be coming toward you while the other goes away. The star that's coming toward you, its spectral lines are all blue shifted. Move down the blue end of the rainbow. The star that's moving away from you, its spectrum will be red shifted. All these spectral lines will be moving down the red end of the rainbow. So the net result is, as these two stars co-orbit their common center of mass, their spectral lines will move back and forth. Both of them, back and forth, back and forth, back and forth across the spectrum. So that's how we know how massive stars are. We use gravity as our measuring stick. And what are the results here? The least massive stars that can full-blown be classified as stars are about 1/12 the mass of the sun, about 0.08. The most massive stars that have been directly measured are about 150 times the mass of the sun. Although there are stars that are not in binary systems where their masses have been estimated by computer models that say they might be up to 300 times the mass of the sun, roundabout. But those are based on computer models. Again, come back when you have data. Computer models are great when they have data to back them up. If they don't, then it's a step. Kind of like Obamacare. It's not universal health care, but it's a step. But the most massive stars that have been directly measured because they're part of a binary system, directly measured using gravity, are about 150 times the mass of the sun. All right. We measure a star's luminosity, or we compute a star's luminosity by measuring its distance using stellar parallax and its apparent brightness, which is easy, right? Apparent brightness is just how much light comes into your telescope. That's one observation, one measurement. We measure temperature by looking both at the brightest color of the star, that'll tell us the temperature, and also by looking at what substances are in the atmosphere of the star, because different substances are stable at different temperatures. If it's got a lot of molecules, why, it's a cool star. If it's got a lot of ionization, that is, if atoms have a lot of electrons ripped off, then it's a really hot star. To measure a stellar mass using gravity, you need two of the three quantities: orbital period, the orbital separation, or the average distance between two binary stars, and the orbital velocities. It's easiest to think of if it's a circular orbit, because then the orbital separation and velocities both stay constant. But even if it's not, even if they have elliptical orbits, you can still measure them. So if you can measure 2 out of the 3, then you can compute the third, and boom, you have it. All right, so that's the method. Those are the methods that astronomers use to study stars. So what patterns come out of this? That's a lot of science, right? Finding patterns. This is the Hertzsprung-Russell diagram. It is, to a stellar astronomer, someone who studies stars, what the periodic table of the elements is to a chemist, right? If you take a chemistry class, and there will be a periodic table of the elements on the wall. The teacher will not expect you to memorize the periodic table of the elements unless the teacher is just sadistic. Most teachers don't. They don't want you to memorize it. They want you to use it. They want you to be able to look up the wall, look at that table, pick the information you need off the table, and then use it in your calculations. Likewise, the Hertzsprung-Russell diagram is not something you will be expected to memorize. It is something you will be expected to use. And let me write this down using my very low-tech notepad here. I'm going to post an HR diagram for you in the file set. Oh, it'll be in the lecture slides. Okay, it'll be in the lecture slides, which will be in the file section on Canvas. So let's look at this. An HR diagram, a Hertzsprung-Russell diagram, is a scatter plot. That is, it has a bunch of dots on it, and each dot is a star. On the x-axis, you have temperature. Hot is to the left, cool is to the right. Well, remember, temperature follows color, so the x-axis is also color. The bluer stars are on the left. Those are really ultraviolet stars. And the redder stars are on the right. And then, again, those are really infrared stars. Also, it follows frequency, right? Color is defined both by wavelength and frequency. So on the left here, you have high frequency glowing stars and low wavelength glowing stars. Over on the right, you have low frequency, high wavelength glowing stars. On the x-axis is also spectral type, because remember, spectral type follows temperature. O is on the left, M is on the right. So there's a crazy amount of information about a star by just where it falls to the left or to the right on the HR diagram. What about the y-axis? Well, the y-axis is luminosity, how bright a star is. Total brightness, not just brightness from each square inch. So the total brightness is going to depend on its temperature, how bright it is from each square inch, and its size, how many square inches it has from which to glow. So at its most basic idea, the HR diagram plots luminosity versus temperature, or spectral type, or color, wavelength, frequency. All of those are plotted on the x-axis. First thing you'll notice is that there's a diagonal line. Okay, it's not quite a straight line, it's more of a curve. A diagonal curve. We call this the main sequence. And most stars are on the main sequence. In fact, most stars are clustered down here at the bottom. If you, stars that are above and to the right of the main sequence tend to be big, large stars, high radius. These are giant stars and supergiants. Whereas stars down and to the left are small stars, dwarf stars. Luminosity class is something that astronomers use to give additional information more than just spectral type. So our sun is a G25. It's a G-type star. 5 means it's a main sequence, and then 2 is just a subtype of G. So it's kind of like our sun has properties that are similar to, but not exactly the same as a G1 or a G3. All right, man. We've got a whole lot of information on the HR diagram so far. We've got temperature, we got color, we got spectral type, luminosity, and radius. All right, here's a thought question. How are we going to do this? All right, give me 100% participation. It's okay to get it wrong. Just think of the idea in your head, or better yet, write it down on paper. I know you don't have to. I can't watch you, but you'll learn a lot more if you engage. So please, write down what you think the answer is, and then high five yourself if you get it right. And if you get it wrong, just think about, why was the right answer right? So which star is the hottest? A, B, C, or D? Think about it. All right, well, temperature's on the x-axis. Left is hot, and the leftmost star is A. So this is the hottest star right there that's shown. Which star is the most luminous? All right, well, luminosity is on the y-axis, which means hottest stars are up top. So the highest star up is C. That is the most luminous star depicted. Which of the 4 stars shown here is a main sequence star? Well, the main sequence is the diagonal curve, and the only star on the diagonal curve is D. All right, well, what's the largest star? Well, large stars are up and to the right, so that would be C. I'm a little concerned here because I have to save this as a low-quality movie, otherwise it crashes my computer. But I'm afraid you might not be able to see this in full resolution. So please open up the, if you can't see the diagonal lines, can you see these diagonal lines? If you cannot, open up the lecture slides, the PowerPoint slides, so that you can see this. This is super important. These diagonal lines are lines of equal radius. They're like stair steps for radius. So down in this region, these would be the smallest stars. Larger stars than that. Up here are larger than that. Every step up, every time you cross a line, the stars get bigger. So the largest stars are up and to the right. So what about this main sequence? What's so special about it? Why are so many stars on it? Why do we care about it? Main sequence stars are still turning hydrogen into helium in their cores, just like our sun is. So as long as a star is born, it becomes a full-blown star when it enters the main sequence, and it more or less stays where it is on the main sequence until it runs out of hydrogen in its core, and then it becomes very unstable and moves off the main sequence. So high mass main sequence stars are at the upper left of the main sequence, the high part of the main sequence. Low mass stars are at the bottom of the main sequence. High mass stars are pretty rare because they blow up very quickly. Low mass stars are very common because they last a long time. All right. I have some family members, an aunt and an uncle, who I used to think were very poor. They kind of lived in a shack. And when they died, the family found $250,000 in cash under their bed. So it turns out, although they lived a very poor lifestyle, they weren't very poor. They were frugal. They wanted their money to last forever. And it did, or at least until they died. All right. Low mass stars are like my aunt and uncle. They are frugal. They burn through their hydrogen very, very slowly. That's why they're not very luminous. They're very dim. They are careful. They are conservative with their money, with their hydrogen. So they last for a very, very long time. The smallest stars have enough hydrogen in them to burn for 1 trillion years, 1 trillion with a T. Let's go up here to the upper end, the high mass stars. The high mass stars are like someone who just won the lottery and spent it all in one day. I just won $1 million. Here, I'll buy a yacht. Now I'm broke. High mass stars burn through their hydrogen very, very quickly. They live fast and die young. The highest mass stars may only live a few tens of thousands of years, whereas the lowest mass stars will live a few 100 billion years or even 1 trillion. So high mass stars are very, very bright because they got a lot of nuclear fusion going on. They are burning through their fuel very quickly. Low mass stars are very dim because they're burning through their hydrogen very slowly, and they last a long time. So the hot blue stars are much, much, much more massive than the cool red ones. And what this means then is that you can determine a star's lifespan. That is, how much hydrogen or how long it will burn its hydrogen based on its position on the HR diagram. The lower down it is, the longer it's going to be able to burn hydrogen. So that's what this lifetime means. The high mass end here, we have 10 to the 7 years. That's 100,000 years. There are more massive stars up here that will last even less time than that. 10 to the 8th years, so then that's 100 million. Here's 10 to the 9th years. That's 1 billion. Our sun is right here at 10 to the 10th years. It has a lifespan of about 10 billion years, and it's already halfway through that lifespan. Doesn't mean the clock doesn't start now. The clock started when the sun was born. A lower mass star than our sun might live 10 to the 11th years. That is 100 million years. And the lowest mass stars of all will live 10 to the 12th, or 1 trillion years or longer. So the properties of a star depend almost entirely on a star's mass, because a star's mass determines how much pressure and temperature there is in the core. The more massive a star, the more pressure and temperature there is in the core, which means the more nuclear fusion is happening in the core, which means the brighter the star is, the bluer it is, and the more quickly it will run out of fuel, the more quickly it will burn out. An exception to that rule is in close binary stars. So a close binary star, the properties of a star can be determined by how close it is to another star. Close binary stars interact with each other, not just with their own mass. So that can get more complicated. All right, so let's look at all the stars that we know of and their ranges of their properties. Luminosities of stars range from 10 to the -4, that is 1/10,000th the luminosity of the sun, up to 10 to the 6th, 1 million times the luminosity of the sun. Stars' temperatures range from about half the solar temperature, 3,000 Kelvin, up to 50,000 Kelvin. It's 8 or 9 times the temperature of the sun. Masses range from 0.08 solar masses up to 100-ish. Okay, they've been measured at 150 and even estimated up to 300. So to put this in an analogy of... Oh, this is not the analogy. Never mind. Masses and lifetimes of main sequence stars. High mass stars, say 10 times the mass of the sun, will burn blue, and it will burn through its fuel very quickly, so it'll only last 10 million years. Our sun is a yellow-green star. It's moderate mass, so it's going to burn through its fuel moderately, and it's going to last 10 billion years. But the tiniest red stars, the little red dwarf stars, the little M dwarf stars that are less than 1/10 the mass of the sun, they're going to last 1 trillion years, because they are very frugal. They burn through their fuel slowly. All right, well, let's recap that. High mass means high luminosity, short lifespan, large radius, and blue. Low mass is low luminosity, long-lived, small, and red. So those are main sequence stars. What about the other stars? What are the stars that are not on the main sequence? For reasons we'll talk about in upcoming lectures, when a star runs out of hydrogen in its core, it becomes very unstable. It changes very quickly. It gets big and it gets smaller and then bigger and smaller. Kind of hard to keep track of. When a star has left the main sequence, we call it a giant if it's a low mass star, or a supergiant if it's a high mass star. Intuitively, a supergiant is even larger than a giant. And then they bounce around the main sequence for a while. Again, we're going to get deep into this slide in upcoming lectures. This is just a preview. When a high mass star ends its life, it explodes as a supernova. and its core is then left behind as a neutron star, which is a giant atomic nucleus, a giant ball of neutrons. Or if it's massive enough, that neutron star will collapse into a black hole, an object in space with so much gravity, nothing can escape, not even light. Now that's pretty dramatic. That's what high mass stars do. But a low mass star, like our sun, will not explode. It will expel its atmosphere out into space to form a nebula, a planetary nebula, and then its core will be left behind as a white dwarf, a dense ball of carbon and oxygen. Here's the metaphor of human life as, here is human life as an analogy for star life. A young star or a middle-aged star, that's a main sequence star, got all its body parts working. The autumn years, when your core kind of runs out of hydrogen and you become a little more vulnerable to coronavirus, that's a red giant if you have a low mass star, a red supergiant if you have a high mass star. And the cutoff between low mass and high mass is 8 to 10 solar masses. There's a margin of error on that cutoff. Once the star dies and is no longer fusing at all, it becomes a zombie corpse. I say a zombie because, it's still glowing. It's not completely dead, but there's no fusion going on. For low mass stars, the zombie corpse is a white dwarf. And that is overwhelmingly the majority of stars, 97%. And the rest of the stars, the high mass stars, become neutron stars. 3% become neutron stars. And when I say high mass, I mean 8 to 10 solar masses up to 25 or 30. Again, there are margins of error on each of these cutoffs. But the most extreme mass stars, 25 or 30 masses or above, will become black holes at the end of their life. So a white dwarf star is very small. It's compact. It's the size of Earth. Only the size of Earth. The mass of a star compacted down to the size of Earth. Remember, the sun is 100 times the size of Earth by radius. So the mass of the sun compacted down 100 times by radius, that's 1,000,000 times by volume, is a white dwarf. White dwarfs are extremely compact by volume. They have been compacted down 1,000,000 times. So a teaspoonful of white dwarf would weigh as much as a pickup truck. Now let's zoom out. This little white dot here is a white dwarf. Let's zoom out to a main sequence star like our sun. All right, that's 1 solar radius, 100 times the radius of Earth. Let's zoom out again, almost to the orbit of Mercury. A giant star may be almost as large as the orbit of Mercury. Some giant stars can be larger than the orbit of Mercury or Venus even. Once you get past the orbit of Earth, you start approaching supergiant phase. A supergiant can be larger than Earth, larger than the orbit of Earth or Mars, or occasionally even Jupiter. So supergiants are, not surprisingly, super big. All right, let's go back to thought question. See if you can get this. Which star is most like our sun? Star A, B, C, or D? Well, you determine this by looking at its position on the HR diagram. And our sun is a G-type star, right there, doop-de-doo, and it is on the main sequence. So right there. There it is. So the star that is closest to our sun on the main sequence, that's where our sun is D. Here's a tricky one. Which of these stars will have changed the least 10 billion years from now? Think and see if you can come up with the answer on that. Did you get it? So some folks, first off, it's certainly not C. C is a red supergiant. Those are really unstable. They swell up and then swell back down and then swell up, and pretty soon they explode. It's certainly not B. It's a high mass star that just left the main sequence. So again, it's going to blow. It's going to swell up and swell down and swell up and swell down until it just explodes. Some students will say D because it's close to our sun. But remember, our sun only has a lifespan of 10 billion years. In fact, D is closer to the 1 billion year lifespan. So after 10 billion years, it's going to be a white dwarf. The one that is not going to change much, the one that is pretty much done in its evolution, the one that is already a zombie corpse, is star A, the white dwarf. White dwarf is not going to go through much more dramatic changes unless it's in a close binary system. Then it can get dramatic. Some crazy things can happen if it's in a close binary system. It can steal mass from its companion star, and either the surface explodes, which we call a nova, or the whole star explodes, we call a supernova. Again, that's a preview. We will look at that in more detail in upcoming lectures. Don't touch your face, people. All right. What will happen to this white dwarf over the course of the next billion years is it will move down the white dwarf graveyard. Why is that? It will radiate away its temperature. It will cool down like a cup of coffee sitting on the table, except it's not steaming, it's just radiating. So as it cools off, it will move downward along the white dwarf graveyard. All right, what is an HR diagram? It is a great thing for exam 3. Last semester, 1/3 of the questions on exam 3 came from the HR diagram. So study the HR diagram very carefully. Make sure you understand what the HR diagram is, how to find information on it. Today's classwork, today's thought questions and the classwork are crucial. An HR diagram then plots the stellar luminosity of stars versus surface temperature. And the x-axis is temperature, but what follows temperature? Color, spectral type. So there's lots going on the x-axis. The main sequence, the diagonal line, diagonal curve, is where stars are still fusing hydrogen into helium in their core. And a star's position on the main sequence is determined by its mass. High mass stars are high on the main sequence, low mass stars are low on the main sequence. High mass stars are bluer, they're bright, they live fast, die young, and explode. Low mass stars are redder. They are faint. They live a long time because they don't burn their hydrogen very quickly. When a star runs out of fuel in its core, for reasons we'll talk about in future lectures, they become unstable. They swell up, they swell back down, they swell up again, sometimes several times. We call these giants if they're a low mass star, and supergiants if they're a big star. And a low mass star, which is 97% of them, will end their lives as white dwarfs. The mass of their core, which is most of the mass of the star, will be compacted down 1,000,000 times by volume to the size of the Earth. High mass stars will end up as neutron stars, essentially a city-sized atomic nucleus, and the most extreme mass stars will end up as black holes. What about star clusters? All right, well, there's 2 basic types of star cluster. One is called an open star cluster. These are beautiful clusters that you can often see with a small telescope. They are loosely packed. They are often young, not always, but often young. They are anywhere from a few dozen up to a few thousand stars that are located in the disk of a galaxy. They were all born together. They're sibling stars. Globular star clusters look like this. You can see these with a small telescope too, and you can often recognize them just by looking because they all pretty much look like that. Globular star clusters are densely, tightly packed. Our sun, our sun is 4 light years from the next nearest star. Inside a globular cluster, stars can be 1 light year or less away from each other. They're densely packed. And there's a bunch of them too. Globular clusters may have tens of thousands of stars, hundreds of thousands, or in extreme cases, millions of stars, all bound together by gravity. And they're not usually inside the galactic disk. Excuse me. They are not usually inside the galactic disk. They are orbiting the disk of the galaxy. And they are old. They are old clusters that were born with the galaxy itself. These stars were born with the galaxy, and there were so many of them, so tightly packed, that the high mass stars among them exploded and drove out the gas. And when there was no gas, there's no new stars. So these things were victims of their own success. They had so much star birth that the high mass stars exploded and stripped the clusters of gas so that they could no longer make new stars. How do we know the age? How do we know how old these star clusters are? Well, it turns out a lot of what we know about the ages of stars comes from studying star clusters, both globular clusters and open clusters. And what we do is plot all the stars on the HR diagram. The low mass stars will almost always still be on the main sequence, whereas the highest mass stars will have already exploded. But what about the intermediate mass stars? The stars that are left on the main sequence are determined by the age of the cluster. The older the star cluster, the more stars will have already left the main sequence. We call this the main sequence turnoff. This is the Pleiades. It's a star cluster very close to the constellation Taurus. I don't know if it's inside that constellation, but Taurus is the bull, and the Pleiades are flies buzzing around the bull. Notice the low mass stars are still on the main sequence. Here they are. The high mass stars are left. There are no stars here on the main sequence. And there's a point at which the Pleiades turn off the main sequence. That tells you the age of the cluster. That tells you the age of the stars in the cluster. Because they were all born together. They were all born from the same giant molecular cloud. So Pleiades now, today, has no stars with life expectancies of less than 100 million years. Right? These are low life expectancies. Up here, they've blown up already. It's got all the stars with life expectancies above 100 million years. So we would say that the Pleiades is about 100 million years old. And we call that point at which a star cluster turns off the main sequence turnoff point. And it tells us the cluster's age. The older the cluster, the farther down the main sequence the turnoff will be. You can think of the main sequence as a zipper. And the zipper is going down. You are undoing the zipper. The lower the zipper, right, the longer it has been in the process of unzipping. So the older the cluster. Here is a globular cluster, and they are old. Look, only the absolute lowest mass stars are still on the main sequence. Even stars like our sun have turned off the main sequence. And our sun only has a lifespan of 10 billion years. So if stars like our sun are already turning off the main sequence, it's got to be about 10 billion years old or more. Globular clusters tend to be as old as the galaxy that they orbit. So for the Milky Way, that's 13 billion years. Another clue that globular clusters are old is from the white dwarfs. Notice most of the white dwarfs are clustered down here in the low temperature section, which means the white dwarfs are old. They've had a long time to cool off, like a cup of coffee sitting on the table. They cool off with time. So, open clusters are loosely packed. They contain a few thousand stars. They're often young. They can be young. They don't have to be, but they often are. Globular clusters are densely packed, and they are old, and they are found outside the disk of the galaxy. They are orbiting the disk of the galaxy. And we tell the age by plotting the stars on the HR diagram and finding the main sequence turnoff. All right, recap it all. We measure the masses of stars by using gravity, by measuring a star's gravitational effect on some other object. Could be another star if it's a binary system, or it could be planets if we can detect planets around that star. And this works if that's a direct measurement, but if we don't have a direct measurement, if we don't detect any planets around a star, or if a star is not in a binary system, I should say, and if a star is not in a binary system, we can still estimate its mass by plotting it on the main sequence, because mass is correlated on the main sequence to color. If it's not a main sequence star, then we got to use more sophisticated computer modeling, which we have only moderate confidence in. Computer modeling is awesome when you have data to back it up. But when you don't have data to back it up, it's just a first step toward understanding something. All right, well, say it with me and make your family wonder what's going on in there. When I say astronomy, you say rocks. Astronomy! Rocks! Repeat after me. No, say it with me. Properties of a star on the HR. The left is hot. The right is not. The top is bright. The largest stars are the upper right. The main sequence spends the weekends fusing hydrogen into helium. Astronomy rocks. All right. Oh, sorry. Yeah, we're not going to do vocabulary quizzes anymore. I mean, wouldn't hurt you to look the stuff up. Well, this is you. I can't baby you anymore. You gotta take it by the reins and own your learning. All right. This is classwork. I'm not going to leave it up here, but rather ask you to download the lecture slides, the PowerPoint slides. Then what you will do, you'll write down the answer. No, please type the answers and upload to Canvas. In assignments, you will see a classwork. If you have any questions, email me. Classwork is due at midnight on Wednesday tonight. Wednesday being March 17th, 18th. Oh, freaking, where's doop-de-doo? Hi, let's look. Let's not say things we don't know. 18th, yes. Midnight on the 18th, classwork is due. Awesome. Talk soon. We'll get through this. If I can figure out how to stop this recording.